I don't want to get too bogged down in the etymology, but if you're gonna name a place the door to hell, it had better look something like this. In this case, I think we can all agree the name fits. The door to hell, otherwise known as the Darvazot gas crater, isn't exactly a natural phenomenon. Nature merely provided the raw materials for what humans managed to turn into a decades-long environmental freak show. And while its origin is somewhat shrouded in mystery, the science behind it is not. It was 1971 when a group of Soviet petroleum geologists set out to explore the Karakum Desert in Turkmenistan. Mostly, they were looking for oil fields, but the region is also rich in natural gas, because oil and gas are both the results of the same geologic process, the very slow, very intense compression of ancient organic material over time. Though there has never been an official report about the events that followed, most believe that during the initial exploration of the area, the geologists were so encouraged by their estimates of how much natural gas there was that they quickly set up some drilling rigs. But unbeknownst to them, they drilled right over a big cavernous pocket of natural gas, and it collapsed soon after the operation began. The ground gave way, taking with it their equipment and creating an enormous sinkhole more than 60 meters in diameter and 20 meters deep. Miraculously, no one is reported to have been killed, but there was another problem. Natural gas is composed primarily of methane, a colorless, odorless gas that, while not toxic, can displace oxygen and easily make it hard to breathe when it's nearby. And then there's that thing that we like so much about methane in the first place. It loves to explode. It can create a combustible mixture in the air at levels as low as 5%. Plus, even though we had yet to pick up on the fact of global warming back then, it's worth pointing out that methane is a greenhouse gas 20 times more potent than carbon dioxide. That's why in some oil and gas drilling operations where natural gas is released, if it can't be captured, it just burns off in the process of flaring. Yes, this still releases tons of CO2, but CO2 is way less bad than methane. Anyway, those 70s Soviet scientists were left with a choice. 1. Continue to let the dangerous methane vent into the atmosphere, putting the local population and environment at risk, or 2. Light the crater on fire, burning off all the gas in what scientists predicted would take a few weeks. They chose the latter, and 42 years later, the crater is still burning. Today, the door to hell has become something of a tourist attraction, creating an eerie glow that can be seen at night from kilometers away and releasing a terrible, eggy smell that has nothing to do with natural gas, which, remember, has no smell, but is instead produced by hydrogen sulfide in the ground. Can't wait to go there myself. And if you want to visit, you probably have some time. The fire will continue to burn until all the natural gas deposits feeding the flame have been combusted. And no one knows when that's gonna happen. Do you have an idea for a weird place you'd like us to teach the world about? Or for any other SciShow episode, let us know in the comments below, and you can also find us on Facebook and Twitter. Would you like to sponsor a graphic with your name on it, or get a SciShow poster signed by the whole crew here? To learn about these perks and more, go to Subbable.com, and don't forget to go to YouTube.com/SciShow and subscribe. Everyone dies! It's kind of a bummer, but it's inevitable. Humans have entire philosophies and religions dedicated to the contemplation of what happens once our bodies stop working. But unless you're a mortician, how much thought do you give to what happens to your flesh and blood after you die? Will it be burned up, buried underground, frozen, probed by queasy medical students, or even displayed in a museum? These days, once you're dead, you actually have a lot of options, with more on the way. No wonder the U.S.
When Alan Shepard became the first American in space,
Remember last August when like half the freaking world was following the final nerve-wracking hours of the Mars Science Laboratory's journey to the Red Planet? It was one of the most exciting days in the history of Mars exploration, also one of the most exciting days in the history of me being a person. And success! The Curiosity rover is still roving in Gale Crater as we speak, studying the planet with its fascinating array of tools, including the mast, camera, and X-ray spectrometer. We are going to learn a lot about Mars from Curiosity, and hopefully some of the data it sends back will help us prepare for future manned expeditions. But what if I told you that the MSL has already given us some of the most important information we need, at least in terms of sending humans to Mars, while it was on its way there? And what if I told you that that data is not very encouraging. You might remember that we've talked before about some of the big picture questions that come up when we start thinking about sending people to Mars. But we love ourselves some Mars exploration, and since then there have been some fascinating developments that may shed light on the feasibility of humans ever getting to the Red Planet. There are a number of puzzles we need to solve in order to safely and efficiently get there, and one of the trickiest is radiation. While it'll certainly be an issue once humans are on Mars, the larger problem is the huge amounts of radiation that astronauts will be exposed to en route. We've learned a lot about this in the last year thanks to Curiosity, which is equipped with a Radiation Assessment Detector, or RAD. Engineers built the toaster-sized device and its sensors with the idea of using them on the Martian surface, but some scientists wisely suggested that if they turned on the instrument during the MSL's 253-day, 563 million kilometer voyage to Mars, it would help NASA learn what radiation levels humans might be exposed to on the trip. And given that the shielding used to protect the MSL is similar to what might be used on a future manned spacecraft, the data could not be more relevant. Radiation doses are measured in units called sieverts, and the results from the RAD published in the journal Science in May of 2013 indicate that astronauts would be exposed to roughly 2/3 of a sievert over the course of a round-trip excursion to Mars. That is a lot. On Earth, humans receive about 1,000th of a sievert per year from outer space, and potentially a few more thousandths from X-rays and CT scans and other man-made sources. Sensors on MSL's radiation detector, which, keep in mind, were protected on the way there, counted the number of energetic particles like protons that hit the instrument, revealing an average dose of 1.84 millisieverts per day. You'd have to get yourself a full-body CT scan at a hospital every 5 days to expose yourself to that level of radiation on Earth, and according to the National Cancer Institute, those 12 to 16 months spent traveling in space would raise the astronaut's chance of dying from cancer from 21 to 24%. That's not insignificant. It also guarantees that a voyage to Mars, including time spent on the planet, would exceed NASA's current guidelines for exposure, which ensure that an astronaut's cancer risk will not increase by more than 3%. Radiation can do a lot of bad things to a body, both in short and long terms. Not only can large doses increase your cancer risk, but it can lessen your resistance to infections, cause short-term memory loss and blindness, and increased risk of heart disease. And these are problems that could start showing up while the mission is still en route. Even worse would be an unforeseen cosmic event like a radiation burst from the sun or deep space that could expose astronauts to much larger doses, resulting in acute radiation syndrome, which can quickly result in organ shutdown and an incredibly horrible and painful death. Obviously, pretty much the last thing on the list of things we want happening to astronauts that are 300 million kilometers from Earth. So, how do we attack this problem? Because we are going to attack it. Well, there are two types of radiation that we have to address. The first are called solar energetic particles, which are emitted by the sun during huge explosions on its surface. You know these events as solar flares or coronal mass ejections. Episodes like these happen fairly randomly, though they are less frequent at quiet times during the sun's 11-year cycle. The MSL traveled to Mars during one of these quiet times, but it still recorded 5 solar particle events. More worrisome are galactic cosmic rays, or GCRs, which originate outside the solar system, usually from exploded stars or the vicinity of black holes. It's actually easier for them to penetrate the solar system when solar activity is low. More unfortunate is the fact that GCRs can also penetrate deep into human tissues and damage our DNA. And shielding a spacecraft from them is not easy. Even a 30-centimeter thick aluminum hull would do little to affect astronauts' GCR exposure, and scientists have found that piling on additional layers of aluminum, polyethylene, or even containers full of water would reduce exposure to solar radiation, but not GCRs. On the Martian surface, radiation exposure is somewhat less of a concern. Data from Curiosity have revealed that astronauts would be exposed to about 0.7 millisieverts per day. That's still not ideal, but it's about what crew members of the International Space Station are exposed to each day. So NASA engineers are naturally trying to develop more effective radiation shielding systems for future Mars spacecraft. They pretty much have to, but the most effective way to limit radiation exposure on the way to Mars would be to build a vehicle that can get there faster. Which leads us to a second challenge: propulsion. Even if we stick with the conventional methods we've used since the Apollo program, chemical rocket engines propelled by liquid hydrogen and oxygen, some enormous hurdles remain. Namely, how do you store that much fuel? In all, about 90% of the initial weight of a conventional spacecraft would be fuel. And fuel is heavy and therefore expensive in terms of both money and energy to move. Making matters even less efficient, mission planners expect to lose a lot of the fuel along the way. The extreme temperature changes that spacecraft experience, particularly when in orbit around a planet, cause some of the rocket fuel to vaporize. Plus, hydrogen is known for its propensity to leak, often at rates of up to 4% per month. So what about unconventional methods, particularly ones that don't involve words like warp and drive? Can I possibly interest you in some solar electric or nuclear electric propulsion? The first isn't even theoretical. We have spacecraft currently exploring the solar system with solar-powered electric engines. Solar electric propulsion, or SEP, generates electric power from solar arrays, which is used to convert neutral atoms of fuel, usually the heavy noble gas xenon, into charged atoms or ions. These xenon ions are then accelerated by magnets to give the engine thrust. NASA's Dawn spacecraft, which launched in 2007 on a mission to study Ceres and Vesta, the two largest objects in the asteroid belt, uses an ion propulsion system just like this, powered by large solar panels. SEP spacecraft engines offer long-lasting thrust, but the downside of that efficiency is a lack of power. Using current SEP technology would probably take several years to reach Mars in a manned spacecraft, and as we just talked about, we don't have that kind of time to be floating around up there. Nuclear-powered electric engines are an intriguing option, but the technology isn't ready yet. Conducting nuclear fission requires a lot of heavy equipment. It also requires hydrogen fuel, which, as we've learned, is not easy to store in the long term. So what about a hybrid of some kind, using elements of traditional chemical propulsion and SEP is an option, though it remains unclear just how much it would speed up a trip to Mars. The idea would be to use chemical rockets to boost the craft out of low Earth orbit, where such a craft would have to be built, and then use an electric propulsion system for the remainder of the trip. If we go that route, we're still going to need larger and more powerful solar arrays than currently exist in order to speed up the trip and lessen all that exposure to radiation. All this, and we haven't even gotten to actually exploring Mars yet. I could do an entire episode on the Martian dust situation, which is going to be really bad for engines, tools, and humans. So it's hard for me to be very optimistic about our near-term prospects for a Mars mission, but there are always private groups that have their eyes on the red planet, though their plans are a little bit far-fetched. We talked about the Mars Society just last year, but others keep popping up. One is called the Inspiration Mars Foundation, whose goal is to send a two-person American crew to fly within 100 miles of Mars and then return to Earth. Their planned launch date is January 5th, 2018, which is when the closest alignment of the planets will allow for a round-trip duration of just 501 days. The nonprofit plans to use conventional technologies for the trip, though there are few details about how all this will be funded and carried out in less than 5 years. Even more optimistic is another nonprofit called Mars One, which hopes to establish a 4-person Mars colony in 2023 with a budget of $6 billion. You may have heard of these guys because A, their plan does not involve humans ever returning to Earth, and B, they recently began taking applications for potential crew members, and more than 76,000 people have applied. Their plan entails launching a series of unmanned supply missions beginning in 2016 to reach Mars before the people who need them will be there. It also entails funding a lot of the mission by selling broadcast rights for different milestones along the way. I'll be honest, I don't think we're going to have humans on Mars in less than a decade. A flyby mission is far more likely, though maybe not in 5 years. And while I still wonder if even NASA's stated goal of sending humans to the Red Planet in the 2030s is realistic, I appreciate the vision and enthusiasm of these nonprofits. We want people to stay excited about Mars exploration, and it says something about the passion we have as a species to explore the universe that we've finally begun to talk about astronauts, possibly citizen astronauts, making the ultimate sacrifice and never coming home just for a chance to touch the surface of another world. So, what do you think? Would it be worth it? Would you even want to do it yourself, maybe? Can you think of another way? Tell us about it on Facebook or Twitter or down in the comments below. And if you want to keep getting smarter with us here at SciShow, you can go to youtube.com/SciShow and subscribe.
the grand scheme of things, we haven't been at the space exploration game very long, but we've already learned a ton about the solar system. We've sent probes to planets and asteroids.
Beyond the reach of our naked eyes, more than 30 times farther from the sun than our Earth, resides a captivating planet, teetering on the edge of the unknown. Neptune, a distant realm so elusive that even the mightiest peaks on Earth fail to capture its celestial grandeur without the aid of a telescope. This remote planet, adrift in the cosmic abyss, has remained the least explored entity within our entire system, harboring secrets that have tantalized scientists for centuries. Its icy expanse, seemingly inhospitable and unyielding, guards a breathtaking revelation. A paradoxical world where one of the coldest planets in our system nurtures an unfathomable ocean of scorching hot water. Today, we embark on a journey to uncover the enigmatic truths of Neptune, delving into its bewitching rings, unraveling the story behind its ethereal azure hue, and unveil the first real images of Neptune and the celestial wonders that lie hidden within its icy embrace. Neptune, the seventh planet in our solar symphony, is a majestic ice giant. With a diameter nearly 4 times wider than Earth, encompassing a staggering radius of 15,300 miles, this awe-inspiring planet boasts of a luminous magnitude that eclipses our home world a staggering 58 times over. Neptune, composed predominantly of water, methane, and ammonia, mirrors its fellow ice and gas giants in lacking a solid surface, instead welcoming us into an ethereal realm where its atmosphere plunges deep into its core. Within this enigmatic ice giant, hidden amidst its frigid exterior, lies a tantalizing possibility. A secret oasis that defies reason. A theoretical hot ocean that defies Neptune's distant proximity to the sun. As sunlight embarks on a 4-hour journey to graze the planet's surface, Neptune remains one of the coldest objects in our cosmic neighborhood, with an average atmospheric pressure plunging to a bone-chilling -360 degrees Fahrenheit. Recent studies reveal Neptune's enigmatic cooling trend from 2003 to 2018, despite peculiar warming near its south pole from 2018 to 2020, likely attributed to the intriguing dance of seasonal changes in atmospheric chemistry. The origin of this clandestine ocean within the icy depths remains an unsolved puzzle, as gravitational compression, gravitational interaction with its satellite Triton, or even a cosmic collision may have ignited its mesmerizing internal heat. While some researchers remain skeptical of Neptune's oceanic potential, positing a mere 15% probability, others speculate that the likelihood increases to 40% in a billion years once the giant cools down. Yet the energy radiating from Neptune, nearly 3 times greater than its solar intake, hints at a cosmic mystery waiting to be unraveled, further amplified by its peculiar 28-degree tilt axis, akin to Earth's own. It is within this enigmatic world, cloaked in perpetual seasons that span a staggering 40 Earth years, where tempestuous winds of unparalleled might roar to life, sculpting a celestial symphony unique to Neptune. As we journey deeper into the heart of this cosmic wonder, we shall unveil the awe-inspiring secrets of Neptune's superpowered winds and unravel the captivating composition of its atmosphere, an 80% hydrogen composition interwoven with 19% helium and a tantalizing 1% of other gases, including the enigmatic presence of methane. Another interesting fact about Neptune is its distinctive blue color, which, like a celestial brushstroke, is crafted with precision by ethereal methane clouds dwelling in its upper atmospheric layers. It is these methane molecules that play a symphony with sunlight, absorbing its shortwave radiation and reflecting a mesmerizing blue color back into the cosmos. However, the nearby planet Uranus boasts a similar distribution of gases, yet its color remains a pale blue, leaving scientists pondering the enigmatic difference. Dr. Patrick Irwin of Oxford University offers a fascinating explanation, suggesting that the density of methane fog may be the key to this chromatic variation. Within the atmosphere of both Neptune and Uranus, several aerosol layers weave an intricate tapestry. The deep bottom layer comprises a mixture of hydrogen sulfide ice, concealing certain regions closer to the poles, casting darker hues upon Neptune's visage. The second layer, a realm of haze particles, likely shrouds methane ice formations, creating an atmosphere ripe for the celestial ballet of precipitation. Methane snow that gently descends like celestial benediction. Yet it is Neptune. Neptune's atmospheric vivacity that sets it apart, allowing for the efficient formation of this ethereal snow, resulting in a thinner second aerosol layer. As we explore further into the realms of Neptune's atmosphere, we shall uncover the final layer, a culmination of large methane ice particles, an extension of the second layer, adding the final brushstroke to this celestial masterpiece. Within the turbulent embrace of Neptune's realm, a tempestuous symphony of storms unfolds, adorning its surface with a mesmerizing tapestry of dark and white patches. These swirling maelstroms, born from the planet's dizzying axial rotation, bear witness to Neptune's status as the unrivaled titan of winds in our solar system. Here, the gusts unleash their fury, reaching mind-bending speeds of up to 1,200 miles per hour, a tempestuous dance 4 times stronger than even the mighty Jupiter. Yet amidst the chaos, a kinship emerges, as Neptune shares one similarity with its celestial counterpart, an awe-inspiring tempest known simply as the Big Dark Spot. First discovered by the Voyager 2 spacecraft in 1989, this colossal cyclone, with dimensions comparable to that of Earth, captivated the imaginations of astronomers. However, its nature proved elusive, for in 1994, the Hubble telescope revealed that the spot had vanished, replaced by a small counterpart in Neptune's northern hemisphere. Unlike Jupiter's enduring 300-year-old cyclone, Neptune's grand-scale vortices are ephemeral, existing for a mere span of 2 to 6 years. Then, in 2018, Hubble's watchful gaze caught another spot emerging, akin to its 1989 counterpart, fueling the curiosity of scientists. Previous observations have shown that such cyclones are accompanied by ethereal white methane clouds, aptly named Scooter due to their swift motion, surpassing that of the primary storm. These clouds, believed to form over vortices where gases freeze into ice crystals, provide valuable insights into the enigmatic patch formations on Neptune and other celestial ice giants. Additionally, Neptune also boasts a remarkable feature like its gas giant counterparts, the presence of a majestic ring system. In 2022, the James Webb Space Telescope treated us to a stunning near-infrared image of Neptune, unveiling its delicate rings and satellites. The previous snapshot of Neptune's rings was taken more than 3 decades ago by the Voyager 2 spacecraft. However, with Webb's technological prowess, we can now glimpse approximately 5 distinct rings encircling the planet. Each of Neptune's rings pays homage to astronomers who have made significant contributions to our understanding of this distant world. The innermost and most diffuse ring bears the name Hall, comprising around 40 to 70% dust. Spanning a radial width of 26,000 miles, this ethereal ring also extends 1,240 miles inwards. Moving outward, we encounter the Leverrier ring, which shines more brightly, but possesses a narrower width of just over 62 miles. Next in line is the grandest of them all, the Lassell ring, stretching an impressive 2,485 miles wide. With a dust content of only 20 to 40%, this expansive ring dazzles with its magnificence. The Arago ring, although challenging to discern, stands as one of the smallest, with a radius of 35,540 miles. Nestled on the fringes of the Lassell ring, its subtle presence may be due to its low dust concentration. Lastly, we encounter the diminutive Adams ring, occupying an orbital radius of approximately 39,724 miles. Its slender width of a mere 35 kilometers earns it the title of Neptune's narrowest ring. Yet what truly sets this ring apart are its captivating arcs, mysterious bright bands of dust encircling its circumference. Each of Adam's arcs bears a distinctive name, such as freedom, brotherhood, courage, and equality. Fascinatingly, these arcs are far from static, engaging in a dynamic exchange of material and altering their sizes. The origin of these enigmatic arcs remains a tantalizing puzzle. However, researcher Emily de Peter proposes a possible cause: the collapse of a parent companion or another celestial object within the Roche limit. Apart from the captivating rings, the James Webb Space Telescope also captured the beauty of Neptune's satellites during its observation. Neptune has a total of 14 moons, categorized as regular and irregular. Webb's lens focused on 6 of the inner regular satellites, including Despina and Galatea, which play a crucial role in forming Neptune's rings by acting as shepherds for the dust particles. However, the most intriguing sight in Webb's image is Triton, the most distant and luminous satellite. In the photo, Triton shines like a brilliant star, even outshining Neptune itself. This peculiar glow arises from Triton's nitrogen ice-covered surface, reflecting approximately 70% of the sunlight it receives. Triton, Neptune's largest satellite, surpasses even the size of Pluto. With a diameter of 1,680 miles, it accounts for 99.7% of the combined mass of all Neptune's moons. Notably, Triton holds the title of being the coldest geologically active object in our entire solar system, with surface temperatures plummeting to a bone-chilling -391 degrees Fahrenheit. This extreme cold arises from its icy, light-reflecting surface. Scientists speculate that Triton did not originate alongside Neptune, but instead evolved in the Kuiper Belt. The Kuiper Belt is a region filled with small and large objects, including dwarf planets like Pluto. At some point, Neptune's gravitational pull captured Triton, causing it to slow down and prevent a collision with the planet. Triton's capture also disrupted the formation of more and larger moons around Neptune. Unlike Jupiter, which boasts nearly 70 satellites, Neptune has a limited number of moons. Triton's peculiarities don't end there. Images taken by the Voyager 2 spacecraft in 1989 unveiled its extraordinary mosaic-like surface, adorned with plumes and craters. Scientists estimate that the surface could be between 10 million to 100 million years old. They also observe smooth regions, suggesting the presence of cryovolcanism and possibly a subsurface ocean. The presence of plumes and depressions akin to lake basins further support the hypothesis of a subsurface ocean. Despite Triton's frigid temperatures, scientists believe that it may retain an abundance of ammonia beneath its surface, slowing down the freezing of water. Furthermore, Triton likely possesses a thin nitrogen atmosphere formed by solar heating. However, it is still too early to determine if life could potentially thrive on Triton, similar to the potential for life on Enceladus. Neptune's connection to the Kuiper Belt, the outer edge of our solar system, raises interesting questions. Without Neptune's gravitational influence, a planet might have formed from these objects. Scientists have observed that some Kuiper Belt objects, including Pluto, are in resonance with Neptune, suggesting that Neptune may have migrated from the inner regions of the solar system. This migration likely helped to retain many Kuiper Belt objects within our solar system. Neptune holds many unsolved mysteries, such as its interior composition and the formation of ice giants. Future scientific expeditions will be crucial in unraveling these enigmas and expanding our understanding of these fascinating worlds. So, is it time to set sail on a daring mission to Neptune? Like, share, comment, and watch more content like this here.
Imagine your surprise if, while flying a kite on a warm spring afternoon, a sudden gust of wind ripped the string from your hand, slicing off your pinky finger. Gross. Now imagine your surprise if several days later, you started growing a new finger, and your severed finger started growing a new you. I'm sure this would be front page news all around the world, but why? The normal way that humans and many other animals reproduce is actually more impressive. You started out your life as a single cell. Once that cell was fertilized, it started copying its DNA, separating those copies and then splitting in two. 2 became 4, 4 became 8, until eventually there were trillions, each doing their own little part to make you who you are today. If a single cell can grow into a full-fledged human, why can't a finger? After all, the chance that a single cell will die or possess some sort of genetic defect is huge, but a finger contains millions of cells. If one or many cells in that finger are defective, the others would be there to take over, right? At first glance, this seems like a better way to reproduce, and it turns out that there are plants and some animals who do reproduce this way. Biologists call it budding. Hydra, for example, are little multi-celled animals found in pond scum. One of the ways they reproduce is by simply sprouting and then shedding a little copy of themselves after having a good meal. Some species of flatworm are able to reproduce through fission. Just like us, they are multi-celled animals. Just like us, each of their cells has its own entire copy of the organism's DNA. Just like us, different cell types, skin cells versus stomach cells for example, are produced by turning specific genes off and others on within those cells. But unlike us, when these animals want to reproduce, if they can't find a mate, they simply rip themselves in half. Both chunks regenerate any missing body parts, and voila, reproduction has occurred. If this is possible, why is it that in humans and so many other animals, evolution bets it all on one single cell every generation? Is this an example of reckless gambling, or did the blind process of evolution actually stumble upon a very brilliant strategy? Stated Clearly presents evolution's hidden wild card, the single-cell bottleneck. When biologists talk about the single-cell bottleneck, they're referring to the strange fact that so many multi-celled organisms start out as a single cell. In sexual reproducers, of course, that single cell, the zygote, is a fusion between what you could call half cells, most commonly a sperm cell and an egg cell, from each parent. Pretty much any animal you'd find at a zoo, so all vertebrates from tiny fish to giant elephants, all insects, and even cephalopods, squid and octopus, all of them use a single cell bottleneck every time they reproduce. Even many species of flatworm, hydra, and other animals that can reproduce through budding and fission, they will occasionally mate and use a single cell bottleneck instead. Why? Restarting each generation as a single cell, that's an extremely complex, extremely risky process. Whenever we find a complex trait like this in biology, this usually means the trait is doing something important. If it wasn't, the relentless filter of natural selection likely would have stopped the process or trait from ever evolving. So what does the single cell bottleneck do for us? What would be your guess? One thing it does for us is it corrects any defects that an adult might have, defects that were caused by bad conditions during development. Charlie here has great genetics. His DNA recipe seems to be nearly flawless, but while developing in the womb, his umbilical cord happened to wrap around his hind leg, dramatically stunting its growth. By the time he was born, the cake had been baked. He now must live his entire life as a tripod. If he ever fathers kittens, that developmental error will be automatically corrected by the single cell bottleneck. Those offspring will have all 4 legs. Likewise, a fresh start can easily correct any injuries and epigenetic glitches that might accumulate through an animal's lifetime, errors that are too complex to fully heal or reverse while an animal is actively trying to live its life. Most importantly, the single cell bottleneck resets a state that scientists call genetic clonality. What is genetic clonality and why does it matter? If you've ever studied wildlife conservation, you probably know that at the population level, genetic diversity is key to the survival of a group of animals. When each individual has a unique DNA sequence, resulting in different traits, this ensures that at least some animals in the group are likely to survive no matter what challenge comes their way. But in many cases, the opposite is true when you compare DNA sequences between cells of a single individual. At this layer of organization, too much genetic diversity can actually lead to problems. The behavior of each cell in your body is influenced by many things, including conditions in the environment around you, chemicals and even parasites that might get inside you, signals from neighboring cells, and the influence of epigenetic markers. But at its core, a cell's behavior depends on its DNA sequence. As cells replicate, mutations can occur in DNA, some of which can change how a mutated cell will behave. 2 cells are considered perfect genetic clones if they have identical DNA sequences. Early on in development, all or most of your cells were perfect genetic clones of the original, but by the time you're an adult, mutations accumulate, meaning the cells of your left hand have slightly different DNA sequences than the cells of your right hand. Some genetic differences can cause conflict between cells. One extreme example would be a lung cell that mutates in a way causing it to rapidly reproduce out of control. In most cases, neighboring cells will eventually stop this from continuing, but if they fail, cancer is born. A less dramatic example would be any mutation that simply causes a cell to misbehave. Liver cells perform a very dangerous job. They help filter toxins from your blood. Conditions can be so harsh inside the liver that it's common for a liver cell to die and have to be replaced before the cell is even 1 year old. Knowing this, imagine a mutation in one of your liver cells that causes that cell to stop helping filter toxins. This might allow that single cell to live a longer, healthier life than its neighbors, but now it's just kind of taking up space and using resources without providing any service in return. The cell colony as a whole, in this example, that colony U, will be slightly weaker as a result. It turns out that our bodies go to drastic measures to stop internal conflicts between cells. In extreme cases, immune cells will seek out and destroy any individuals behaving as if their DNA has mutated too far from the norm. An easier, far less violent way to ensure that each cell shares the same DNA is to start each generation through a single cell bottleneck. Even though it might seem wild to gamble all hope on a single cell, the rewards often do outweigh the risk. If that single cell happens to have a negative mutation, the new organism will often fail to develop early on, allowing the parents to simply try again. On the other hand, if that single cell happens to have a beneficial mutation, that beneficial mutation will end up in every single one of the new organism's cells. To hedge their bets even further, in many animal species, individuals carefully choose who they'll mate with. They tend to prefer partners who are healthy or who are otherwise doing well in the struggle for existence. On top of this, each male in many species produces and releases millions of sperm at a time that must race each other to fertilize a single egg cell. The genes inside each particular sperm cell are the genes that built that particular sperm cell. This means a competition between sperm is a competition between genes. Only those containing the best cell-building genes are likely to fertilize the egg. Biologists who study the mathematics of natural selection have found that single-cell bottlenecks are so useful, it's not clear how some animals get by without them. A collaborative project between scientists at Oxford, Stanford, and the Max Planck Institute of Göttingen are currently studying a population of flatworms that, so far as we can tell, never use single-cell bottlenecks. They strictly reproduce through fission. Is this population doomed to slowly degrade through mutational knockdown? Or have flatworms evolved ways to effectively work with or even benefit from genetically diverse cells? Finding the answers to mysteries like this not only helps us better understand the world around us, but could lead to breakthroughs in the treatment of things like cancer and aging. So to recap here, at first glance, reproducing through a single-cell bottleneck seems like a dangerous, wild gamble, but it actually does many things for us. Among them, it prevents conflicts from popping up between cells by resetting genetic clonality every generation. This reset is so essential, scientists are currently trying to understand how some flatworms and other animal populations seem to survive without it. I am John Perry, and that is the single-cell bottleneck, stated clearly. This video was funded in part by a grant. Stated Clearly presents Stated Clearly presents What is an atom and how do we know? Atoms are the fundamental building blocks of chemistry. Just like baked goods are made of a collection of different types of ingredients, matter itself is made of a collection of different types of atoms. Scientists have discovered 118 kinds of atoms, which we call elements. You can find them laid out on a chart called the periodic table. All things from the screen this video is displayed on to the eyeballs with which you're watching it are made of atoms. But a single atom is so small, it is impossible to see with the naked eye. So there you have it. A random voice from a video you found on the internet claims that everything is made from invisibly small atoms. You may now blindly accept this as fact and happily move on with your day, right? No? Now you are extra curious? You want to know for yourself exactly why it is that scientists think they know that atoms exist? Well, to find out, we must travel back in time to ancient Greece. Meet Democritus, the man that many historians credit for first clearly proposing the idea of an atom. In his day, it was thought by some that if you were to chop up a piece of matter, an apple for instance, you could just keep on chopping forever and ever. There was no end to smallness. For reasons not fully agreed upon by historians, this concept did not sit well with Democritus. Instead, he insisted that at some point, you would reach particles so small and so indestructible they could not be divided any further. He called them atomos, or atoms, which means uncuttable. Now, Democritus didn't actually have any evidence to back up his claim, and because of that, many people simply rejected it. After all, that which can be asserted without evidence can also be dismissed without evidence. Let's fast forward several hundred years and hop on over to the Arabic world. You probably know that salt can be extracted from seawater by simply letting it evaporate or boiling it dry. People have been doing this forever, but alchemist Jabir ibn Hayyan and those that followed his work took the science of extraction to a whole new level. Through careful experimentation, they developed complex processes of filtration, boiling, vapor collection, and cooling. They found that crude starting materials could be divided into multiple incredibly pure substances. Pure meaning they appeared to be consistent all the way through, unlike the complex mixtures of matter often found in nature. In the 1700s, a French husband and wife scientific duo, Marianne Poltz and Antoine Lavoisier, studied and built upon the work of their Arabic predecessors. They found that certain pure substances could be broken down even further through chemical reactions. Water, for example, can be boiled into steam, which is still water, but it can also be split into two pure gases, hydrogen and oxygen. No matter how hard the couple tried, however, they could not reduce oxygen or hydrogen into simpler gases. They concluded that the gases must be elements, foundational substances that cannot be created by mixing other chemicals together and cannot be broken down any further. With this concept in mind, scientists everywhere began searching for and listing as many elements as they could, eventually discovering all 118 listed on the modern periodic table. Some, such as oxygen and hydrogen, are gases at room temperature. Others are solids, such as elemental carbon and gold. Others still are liquid at room temperature, mercury and bromine. It was also found that under the right conditions, pressure and temperature, certain elements will react with each other upon mixing to form new substances with new properties. These are called compounds. The elements oxygen and iron can react to form a brown powder known as rust. Oxygen and mercury react to form a toxic orange powder. Oxygen and hydrogen react to form a clear, refreshing liquid. You probably know it as water. Though the steps may be complicated, all of these reactions can be reversed. Elements can be re-separated, and the amount of each element we get back after separation is always exactly equal to the amount that had reacted to form the compound in the first place. Wonderful. Elements are real, and they appear to be essentially indestructible, but what are they made of? If you were to zoom in on one, a chunk of pure gold for example, can you just keep zooming in forever and ever, seeing nothing but pure gold for infinity? In the early 1800s, a school teacher from England named John Dalton grew fascinated with chemistry. Along with conducting several experiments of his own, he read about every experiment he possibly could, paying special attention to the quantities of each element used up in every chemical reaction. In these numbers, he was surprised to find a pattern emerge. When two elements can react to form multiple types of compounds, they always do so in small, whole number ratios. In this example here, we see that in order to transform a gram of carbon into pure carbon monoxide, we need to add 1.33 grams of oxygen. To turn a gram of carbon into pure carbon dioxide, we need to add exactly twice as much oxygen. That's 2.66 grams. This, and many other similar observations, strongly suggest that oxygen and other elements are made of tiny, indivisible units. Atoms. He didn't know exactly how small an atom was, but the numbers suggested that the atoms of a single element were all nearly identical in size to each other, but different in size to the atoms found in other elements. In 1808, he wrote a 560-page book that briefly mentioned his discovery. It even came with some quite beautiful drawings. While scientists weren't fully convinced that atoms were real, they did find the concept of atoms extremely useful. It helped them make accurate predictions and perform cleaner chemical reactions. In 1905, Albert Einstein, hold on there, in 1905 he was quite a bit younger than that. There we go. In 1905, Albert Einstein proposed an experiment and produced an equation that could be used not only to confirm the existence of atoms, but to determine exactly how big they are. A few years later, French physicist Jean Perrin, or I guess in French that would be something a little more like Jean Perrin, used Einstein's concept to actually do the experiments, confirming beyond reasonable doubt, at least to other physicists and mathematicians, that atoms do in fact exist. Now, if you happen to love math and possess an in-depth understanding of physics, then great. You can just turn off this video right now and go read his book. But for the rest of us, a little visual confirmation that atoms actually do exist would be nice, right? Unfortunately, individual atoms are far too small to be seen with normal light. The wavelength of light is just too great. This means that normal microscopes cannot see atoms. In the 70s, a group of engineers led by Gerd Bennig and Heinrich Rohrer began working on what they called the scanning tunneling microscope, a microscope they hoped would let us take undistorted images of many different types of atoms. It uses a process called electron tunneling to scan and essentially feel the surface of the sample, much like you can feel around in the dark to get a picture of your surroundings. This is an actual scan of silicon atoms forming the surface of a crystal. The colors here are artificial, but this is real data showing the actual pattern of silicon atoms arranged in the sample. Later work by Dr. Wilson Ho improved the technique and cleaned up the presentation of data. While, quote, feeling the atoms does give us good information, researchers still wanted more. A group led by Dr. Ara Apkarian of the National Science Foundation's Castle Research Center discovered a way to use actual light to see atoms. In the past, this was thought to be impossible because the wavelength of light is so much larger than an atom, but by shooting light at the tip of a probe in a modified scanning tunneling microscope, they were able to essentially shrink the light's wavelength and get it to scatter off the sample onto a detection screen. By moving the sample bit by bit, hitting it with light again each time, they were able to piece together this image of a single nitrogen atom, each pixel representing an individual data point from the scan. If we smooth it out, sharpen the edges, and change their chosen color scheme, it is shocking to find how close John Dalton's old drawings actually were to reality. Our species has finally done it. Over 2,000 years after Democritus first proposed the idea of an atom, we have now received direct visual confirmation. Atoms exist. So in summary, what is an atom? Atoms are the fundamental building blocks of chemistry. How do we know they exist? Through chemical reactions, we can witness their effects. Through mathematical equations combined with indirect observations, we can calculate their various sizes. And finally, with the aid of new technologies such as the scanning tunneling microscope, atoms can now be seen. While the word atom technically means uncuttable, we'll see in the next animation that atoms actually can be split apart. Atoms themselves are made of smaller pieces. I'm John Perry, and that's how we know that atoms exist, stated clearly. Well, folks, there we have it. That was the first animation in my 4-part series on the basics of chemistry, the fundamentals of chemistry. Hope you enjoyed it. If you did, subscribe to this YouTube channel and click the little bell icon. That makes sure that you'll see the next Stated Clearly presents... What are atoms made of? As we learned in the last animation, the word atom means uncuttable, and when John Dalton first discovered evidence that atoms exist, he gave them that name because he genuinely thought that they were uncuttable. He thought they were fundamental particles, the smallest bits of matter that exist. Well, it turns out that he was wrong. Atoms can be split apart. They are made of subatomic particles, most importantly, electrons, protons, and neutrons. Protons and neutrons appear to be made of smaller particles still, and truth be told, we don't know for sure if there really is an end to smallness. Reality might just keep going on forever and ever the further you zoom in. So, there's something strange to think about. This image was made of data collected from an actual scan of a single nitrogen atom fixed to a metal surface. What we're actually seeing here is the outside of what is called the electron cloud, the outer edges of the atom. The colors here are artificial, but this is the real shape of a nitrogen atom. Here to the right, we see a simplified model of the same nitrogen atom. This type of model is called the Bohr model, named after the physicist Niels Bohr. Other models do exist which are more accurate, but when first being introduced to chemistry, the Bohr model is the easiest to make sense of, and so it's what we will be using here. In the center of a nitrogen atom, we have the nucleus. Looking over at the scan, you might think that the red section is the nucleus. That's actually not the case. As mentioned, the colors here are artificial. The red pixels are just the part of the electron cloud that's closest to us. The nucleus is hiding underneath the electrons. It is the core of the atom. And in our model, the nucleus has been dramatically enlarged so that we can actually see it. If the model were actually drawn more to scale, the entire nucleus would be smaller than a single pixel on your screen. In fact, if we were to enlarge the atom to the size of a professional soccer field, well, actually the size of 10 professional soccer fields, the nucleus would be about the size of a house spider. The nucleus consists of one or more protons, and in most atoms, a collection of neutrons. Protons and neutrons are what give the atom most of its weight, or its mass, technically. For example, a gold atom has 79 protons and typically 118 neutrons. This is far heavier than a nitrogen atom, which only has 7 protons and usually 7 neutrons. The number of neutrons in a particular type of atom might vary between individuals. For example, while most nitrogen atoms have 7 neutrons, some have just 6, while others have 8. Changing the number of neutrons inside of an atom won't really do much to change its chemical properties. Instead, it will often just make the atom slightly heavier, slightly lighter, or sometimes it will make the atom unstable. On the other hand, if you were to add or subtract just a single proton from nitrogen, assuming you had the technology to do so, you would completely change its chemical properties. So much, in fact, that we would no longer call it nitrogen. Adding just a single proton to a nitrogen atom would transform it into an oxygen atom. Taking a proton away from nitrogen would transform it into carbon. In other words, the number of protons an atom contains determines the type of atom it is. When you look at the periodic table, you find that each element has a number. Hydrogen is number 1, nitrogen is number 7, gold is number 79. This number tells you how many protons a single atom of that element contains. Protons are positively charged, neutrons are neutral. Obviously, they don't actually have little faces on them, but it helps to remember. Electrons, on the other hand, are negatively charged. We often depict them as little particles in orbit around the nucleus, similar to planets orbiting a sun, but this is not technically accurate. Scientists tell us that electrons can be best described as wave functions. Cloud-like structures that sort of resemble the energy force fields you might find in a science fiction movie. That said, for our purposes today, the simplified model actually works best. In general, the number of electrons an atom contains is equal to the number of protons in its nucleus. This is because each positively charged proton attracts one negatively charged electron. Through chemical reactions, however, an electron can sometimes be stripped away from an atom, or an extra electron can sometimes be added. In these cases, we call the modified atom an ion. Okay, that was a lot of information thrown at you in a very short amount of time, so let's just recap here and summarize the most important bits. What exactly are atoms made of? In the center of an atom, we find one or more protons, and in most cases, we also find
On September 15, 1940, the Luftwaffe began a ferocious campaign targeting London. A sudden change in tactics, focusing the full might of their air force on the most heavily populated city in Great Britain. Over the course of this brutal day, over 1,100 German aircraft entered British airspace, an astonishing invasion to attack a non-strategic civilian target. However, this was all part of the Luftwaffe's plan to gain air superiority in British skies, baiting British fighter planes into the sky to face off against their German counterparts. A showdown to eliminate the Royal Air Force as a threat, to pave the way for a German amphibious invasion of Britain. On this first day of the infamous Blitz, over 1,000 aircraft on both sides tangled in the skies above London. The Luftwaffe believed the RAF were on their last legs, but that couldn't have been further from the truth. The Spitfires and Hurricanes, being manufactured in astonishing numbers, outpacing the attrition of the battle, rose to meet the challenge. The pilots of the Luftwaffe flying the Bf-109 were astonished at the resistance they met. However, another number from this period stands out to me. Over the course of this month, the 6th Anti-Aircraft Division, covering the Thames Estuary, the main approach to London from Europe, expended over 250,000 anti-aircraft rounds in its effort to protect the citizens of London. A bewildering 1,800 rounds were needed to take down a single aircraft on this day, according to official records. These numbers are largely accepted by experts as false, with actual rounds needed much higher. Many downed German aircraft claimed by anti-aircraft crews were in fact shot down by fighters in the sky. The cause of these false reports and anti-aircraft technology's ineffectiveness were the same. So, why was anti-aircraft technology during the Battle of Britain so ineffective at damaging invading planes? And how did an ingenious top-secret technology introduced in the middle of the war change the face of the battlefield forever? At the outbreak of the war, anti-aircraft technology was, for the most part, a deterrent. A weapon that became vastly more effective at lower altitudes, and in turn forced enemy aircraft high above the clouds, where they themselves struggled to hit the mark. The task of accurately targeting a high-flying aircraft from the ground was an even more immense challenge. In the best-case scenario, anti-aircraft crews had a direct line of sight with their target, allowing them to estimate both altitude, bearing, and speed. This information was used to aim their barrels to a location in front of the formation's current location, an educated guess of where they would be when the shells arrived. To make this task even harder, Allied fuses had to be timed on the ground, turning a dial on a mechanically timed fuse. Calculating the time it would take for the round to reach the target in the heat of battle was difficult. These calculations needed to be incredibly accurate, allowing the anti-aircraft rounds to explode in close proximity to their target. This variable was also subject to change, as pilots were instructed to change their altitude and bearing randomly to make it impossible to predict flight time and future location. This was a game of chance, and as such, relied on an incredible volume of fire to stand a chance of damaging their target. This problem needed to be solved, and was high on the mind of the British as they held through the brutal storm of this bombing campaign. For anti-aircraft rounds to become vastly more effective, they needed a way to detect their target. In the era of fragile vacuum tubes, building an electronic device capable of surviving the immense 20,000 G acceleration launch out of a gun barrel was a task that was deemed impossible. Work began on radar-triggered fuses in both Britain and Germany before the war broke out, and both abandoned the idea completely for gun-launched projectiles, seeing no way to overcome the technical challenge of ruggedizing the electronics while miniaturizing them to fit into a small artillery shell fuse. However, the Americans persevered and came up with this, the VT fuse, with its ominous red vial of liquid at its core, serving a vital purpose. The challenge of finding a suitable power source for this radar transmitter was another challenge facing the engineers. Early versions of the proximity fuse utilized existing dry cell battery technology, but these came with two huge issues. Their charge would fade in just 2 to 3 months, making long-term storage of these fuses impossible. And secondly, the risk of having power accidentally connect to the transmitter and receiver was far too high. A single failure point could explode an entire ammunition stockpile. For a reminder of what that looks like, this is not a nuclear bomb. This is the SS John Burke, a United States ammunition transport ship that was struck by a Japanese kamikaze bomber while transporting ammunition to the Philippines in 1944. The war in the Pacific was the driving force for the invention of the proximity fuse. The US were losing an astonishing number of ships to Japanese aerial attacks and desperately needed a better way to defend their ships with anti-aircraft fire. The solution the US National Defense Research Committee came up with to solve this issue of safely powering this device was as bizarre and unique as it was ingenious. The engineers switched to a wet cell design. This red vial contains the electrolyte of the battery. This allowed for an ingenious workaround for both problems. The liquid electrolyte was stored inside the battery, separated from the solid plates of the battery inside this vial. Underneath this glass ampule lay a breaker that contained a clever mechanism. 2 levers were pushed towards the center of the mechanism by a spring. When the round began to spin at 50,000 revolutions per minute as a result of the rifling in the gun barrel, these levers would be forced out, which released a trigger, allowing a small explosive primer to force a spiked plunger to break free and strike the glass ampule, breaking it and releasing the electrolyte into the battery. The plates of the battery were composed of thin zinc plates coated in carbon on one side, each layer separated by a plastic insulating ring, and each disc had holes punched into it to allow the electrolyte to flow and fill each layer. This glass could, of course, break with rough handling, but the electrolyte would not fill the space between the battery plates without the centrifugal force of the round forcing the liquid outwards into the surrounding plates. Other safety measures were incorporated to make absolutely sure that the chances of an accidental detonation could only happen when the round was in the air and spun at tremendous speeds. Once energized, this battery would provide power to the oscillator, which generated a continuous sine wave radio current to the transmitter. For space efficiency's sake, the antenna operated as both a transmitter and receiver. With the currents traveling through the same antenna, the fuse needed a way to differentiate between the signal sent and the signal received. For this, the engineers could turn to the Doppler effect. As the target and fuse are traveling towards each other, we can easily calculate the apparent frequency shift due to their relative velocity. Then, with some basic math, we can come up with this equation, subtracting the reflected frequency from the actual frequency. This was called the beat note. This beat note is what the fuse used to detonate the round. The amplitude of this beat signal would also grow as the round approaches the target, providing a signal that looks something like this with amplification. The fuse was tuned to explode at the optimum distance and angle away from the target by tailoring the radar sensitivity to match the fragmentation pattern of the shells. When the round approached the target, the returning radar waves would generate the necessary threshold voltage to trigger the thyrotron, a type of high-speed electrical switch. It looks a lot like a vacuum tube, but it was filled with a low-pressure gas like hydrogen. When a voltage of sufficient magnitude was passed from the amplifier to the cathode grid of the thyrotron, it would ionize the gas inside and allow current to flow to the anode through its glowing cloud of ionized atoms, completing a circuit to a capacitor that in turn would detonate the high explosive charge in the round, creating a cloud of shrapnel at the optimum distance away from the target. This whole assembly, consisting of the vividly red electrolyte capsule, the zinc-carbon battery plates, oscillator, antenna, amplifier, and thyrotron, was then inserted into the fuse body, and the cavities of the fuse were filled with a microcrystalline wax for moisture protection and, critically, mechanically support the electronics to keep everything in place during launch. Packaging this all in a fuse this small in the 1940s was no easy feat. The tubes manufactured for the proximity fuse were drastically smaller than existing conventional tubes. This, of course, helped immensely with resisting the force of launch. With 20,000 Gs of acceleration, every extra gram of weight saving makes the difference. With this multiplication of mass, a single gram would weigh 20 kilograms. The engineering challenge of ensuring every gram of mass inside this fuse was supported by a structure capable of bearing 20 kilograms was immense. A challenge that deterred both the British and Germans, and its success drastically changed the face of the battlefield. The impact this fuse had on the war cannot be overstated. The atomic bomb was the punctuation mark of this worldwide war, but the statistics back the VT fuse as the most impactful invention of the war, an invention that changed the narrative of the war completely, a counter to the newly invented airplane, causing havoc across every theater of the war. Such importance was put on this invention that it was classified as top secret and only approved for use in the Pacific, where any unexploded rounds would be lost to sea. Much of the manufacturing was performed in smaller sub-assemblies to minimize any knowledgeable manufacturer from deducing the purpose of the device, and for good reason. During the London Blitz, it's estimated that 1,800 rounds were needed to take down a single aircraft. But with the introduction of the VT fuse, this number lowered to an average of 85 to 100 rounds, a 10 to 20 times increase in lethality. A jump in lethality that great is akin to the introduction of the machine gun. This was, beyond a doubt, a game-changing invention. At the peak of their production, over 250,000 of these fuses were being manufactured a week. The VT fuse was first fired on January 4th, 1943 on board the cruiser Helena, defending itself from an aerial assault and successfully shooting the aircraft down. This device had a devastating effect on the aerial battles of the Pacific. Japan soon began to run low on trained pilots, and a year later began the kamikaze campaign, sending waves of untrained pilots towards American ships in the hopes just one could get through. In May 1945, 2 destroyers off Okinawa found themselves the targets of 150 kamikaze aircraft. Every single one of them was shot down, a feat that could not have been achieved without the radio proximity fuse, allowing the guns of these boats to fire relentlessly, accurate fire with no pauses to fiddle with mechanically timed fuses. Had the VT fuse been available during the Battle of Britain, the battle would have been even shorter lived, with the anti-aircraft guns of London suddenly becoming an order of magnitude more effective. The swarms of the Luftwaffe bombers would have stood little chance of returning home. It was finally approved for use over land for the first time in conjunction with the Allied invasion of Normandy, a week before Germany began bombarding Britain with the V1 buzz bomb. At its peak, 100 V1s were launched towards Britain, and with the help of the VT fuse, 80% of these automated missiles were shot down. The VT fuse also played a pivotal role in the Battle of the Bulge, allowing artillery fire to explode at the perfect distance overhead, showering the canopy of the Ardennes forest with deadly shrapnel, repelling Germany's final large-scale counter-offensive of the war. Even at this stage of the war, with Germany on the retreat, the VT fuse was a closely guarded secret. Each and every fuse needed to be tracked and accounted for, with one story of artillery officers spending hours searching through snow to locate lost fuses during the Battle of the Bulge, only for them to be returned to them by locals. World War II was defined by technological progress. When the entire world was at war and nation's very survival was at stake, innovation was placed at the very pinnacle of national interests. And this is the reason I find the war so fascinating. I have created 2 series, The Logistics of D-Day and Battle of Britain, detailing the innovations that helped win these critical battles. I put little focus on the military tactics or individual soldiers on the ground. This is the view of these battles from the perspective of an engineering nerd. The logistics of transporting tanks across the English Channel, how the giant game-like board at the centre of RAF Command worked during the Battle of Britain, and the final episode of the Battle of Britain shares the astonishing manufacturing innovations that allowed Britain to out-manufacture Germany in fighter planes and prevent aircraft attrition from affecting their ranks. If you are an engineering nerd like me, these are the series for you. If you want to watch these series, the only place you can find them is Nebula, the streaming platform I created with some of my closest YouTube friends. It's absolutely packed with fantastic engineering content creators. Mustard has this
Hey you, sitting there all slouchy. You gotta fix that posture and straighten out your spine. Well, maybe not completely. Your spine has all these curves in it, so it's not really straight in the first place. Actually, with how your spine is naturally curved, how do we even know what good posture is? Turns out it's pretty difficult to define, but we do know that some types of bad posture aren't so great for your health, and it all has to do with your spine. The spine is one of the most important structures in the human body. It serves as the central support, and it protects the nerves in your spinal cord, allowing your brain to communicate with your muscles and organs. That's why it's so important to take care of your spine. If you don't, there can be drastic consequences. A massive 2010 study on the global burden of disease estimated that lower back pain causes more global disability than any other condition, affecting nearly 1 in 10 people worldwide. To understand what causes this sort of back pain and how posture fits into the picture, you have to understand the shape of your spine. Your spine isn't perfectly straight. The bones, which are called vertebrae, aren't stacked neatly on top of each other. Instead, your spine is curved in an S shape, so the load from your torso is centered directly over your hips. Two parts of the spine curve outward like a turtle shell. Physiotherapists call this kyphotic curvature. These sections are also called primary curves because they have the same shape from fetal development to adulthood. But you also have secondary curves, which start kyphotic and slowly change after birth until they curve the other way, which is called lordotic curvature. The neck starts to switch when an infant can lift their head, and the lower back takes shape when they begin to walk. These secondary curves shift the center of mass of a child's head and torso over their hips and feet, which makes balance easier while standing. Now, these spinal curves can also change in adulthood. For instance, when someone is pregnant, their lower back will become more lordotic to account for the weight of the fetus. In addition to bigger curvature, certain regions of your spine also have some subtle lateral curves and rotation to account for all the organs you're hauling around. Interestingly, people with a rare condition called dextrocardia have hearts on the right side of their torsos, like a mirror image, and they also have mirrored spinal curves to account for the different weight distribution. All this to say, your spine is clearly supposed to be curved in certain ways, but unfortunately, there's not a gold standard for posture to accommodate these curves. For starters, many claims about sitting with proper posture aren't universally supported or strongly backed by science. For example, simply changing your sitting posture doesn't seem to have a major impact on your baseline metabolism, so you won't be able to get shredded just from sitting at your desk in a certain way. To make things even more complicated, many physiotherapists don't agree on what the best posture should look like. So these days, experts are more likely to suggest regular movement and varying posture. You may have noticed that standing desks have become pretty popular, and on its own, extended standing hasn't been shown to be any better than extended sitting. But mixing up your daily routine with sitting, standing, and walking has been found to reduce the incidence of lower back pain in some people. However, it's also important to acknowledge that some people, like those who use wheelchairs, may not be able to adjust their posture that way. Studies have shown that providing lower back support can increase wheelchair users' lung capacity and flow. That can be really important for people who can't breathe as easily. In addition, wheelchair backs that support spinal curves can give users more vertical range of motion of their arms and make it easier for them to push their wheelchairs forward. So we don't really have a definitive best posture, but therapists have identified a couple signs of bad posture that can cause back problems, whether you're sitting or standing. The classic example of bad posture is slouching, and for good reason. Bending forward while you're sitting reverses the curvature of your lower back, making it more kyphotic. An easy way to fix this is to scoot to the back of your chair, which helps realign your vertebrae. And despite the wonders of smartphones, like being able to watch YouTube from anywhere, they've actually led to a new type of bad posture. So-called text neck is what happens when people are using a cell phone or looking at a computer monitor that's positioned too low and bend their neck sharply. This posture fights against the normal lordotic curvature of your neck and can lead to pain. To avoid this, you might just need to position your screens closer to eye level so you're not bending your neck so much and can preserve those smooth spinal curves. Of course, we aren't doctors here at SciShow, so if you are concerned about any pain, a physical therapist can prescribe exercise and posture aids to help your muscles and spine. That's their job, not ours. Sorry if you're super aware of your sitting posture now, but thanks for learning all about spines and support with us here on SciShow. And if you want to support our team and help us provide free, fascinating science content every single day, you can go to patreon.com/scishow.
They might not have adamantium claws or the ability to control the weather with their mind, but genetic superheroes may walk among us. These are people who should have serious genetic diseases according to mutations in their DNA, but they don't, and we don't know why. With more research, scientists working on the Resilience Project are hoping to discover new biological factors that protect humans from disease, or even new treatments for people who are living with these life-threatening conditions. In a study published last week in Nature Biotechnology, the researchers analyzed small sections of nearly 600,000 human genomes, or personal DNA sequences. All of these data came from people who chose to use DNA testing companies and anonymously donated their information to science. After a careful screening process, the scientists found 13 adults with mutations known to cause 8 different debilitating and sometimes lethal childhood diseases. And here's the catch. They all had healthy medical records. One of those diseases was cystic fibrosis, where a mutated gene causes excess mucus production in the lungs and other organs. This can make it really hard to breathe or absorb any nutrients, plus lots of other painful symptoms. Other more rare conditions cause defects in skull and facial development or severe autoimmune problems, and some are almost always lethal in childhood. And also, there must be things that scientists don't quite understand about these diseases. Ideally, we'd like to learn more from the full genomes and other biological samples of these so-called genetic superheroes, but unfortunately, nobody knows who they are since all the DNA data were anonymous. And the consent forms that these 13 people signed don't give the researchers permission to recontact them. So, in a way, their secret identities are intact, and they may never know how special they are. This does also make these findings somewhat speculative, though. After all, without actually meeting these people to collect more data, the researchers can't double-check their results or prove that there weren't errors in the health records or DNA tests. However, the Resilience Project hopes to recruit more people who are happy to be recontacted if they turn out to be genetic superheroes. You may even be one yourself. But let's move on from our genes to our brains. Last week, research groups based in the UK broke through decades of scientific silence and published 2 separate sets of findings that, for the first time, used modern brain imaging to scan people tripping on LSD. LSD, or acid, is one of the best-known psychedelic drugs. A dose of LSD can cause visual hallucinations as well as a sensation known as ego dissolution, where the sense of self slips away, leaving a feeling that's been described as oneness with the universe. LSD was widely studied in the 1950s and 60s before it was banned pretty much everywhere. But these days, it's hard to find funding for any experiment involving illegal drugs, even carefully designed experiments that get specifically licensed by multiple ethics committees and could help us learn new things about our brains. And no funding usually means no science. The trouble is, the field of neuroscience has advanced a lot in the past 50 years, which means there's a huge gap in our knowledge about the possible harms or even therapeutic benefits of drugs like LSD. For the studies released last week, the authors got around these problems by getting all the proper legal permissions, plus partly crowdfunding their research through Wallacea, which is like Kickstarter for science. For the experiments, they recruited 20 people with prior experience using psychedelics, hooked them up to a bunch of brain tracking machines, and injected around 1 recreational dose, 75 micrograms of LSD. Then, the participants recorded their experiences as best they could. The researchers compared these descriptions to the brain scans to try and piece together the inner workings of tripping out brains. Mostly, the hallucinations seem to affect activity in the subject's visual cortex, an area that normally deals with vision. After a dose of LSD, the visual cortex received more blood flow and started communicating more with regions nearby. There was also a drop in strength of the alpha brain waves, which could be connected to a drop in inhibition. Basically, the brain was freewheeling, generating vivid images even when people shut their eyes. And then there were more widespread changes. They found that LSD increased interactions between brain regions that often don't talk to each other, while the brain's busiest communication superhighways got quieter. One of the researchers described the effect as being kind of like a unified, more integrated brain, rather than the usual more distinct sections, and a unified brain was strongly linked to a feeling of ego dissolution. Overall, the scientists who carried out the studies believe more research about LSD's effects on the mind reveal more about consciousness itself. They also hope that the success of these trials will encourage more carefully conducted research into other illegal drugs so we can understand them better. Thanks for watching this episode of SciShow News, which was brought to you by our President of Space, Tariq. If you want to be President of Space and help support the show, just go to patreon.com/scishow, and if you just want to keep getting smarter with us, you can go to youtube.com/scishow and subscribe. Yes, they infected 6 of these organoids with Zika and left 6 uninfected. When they measured the organoids after 11 days, the infected ones were only about 60% as big.
A little while ago, we made a compilation video where we answered your most pressing dog questions. But we here at SciShow are pet non-partisans, so naturally,
Stated Clearly presents What is a molecule? Though textbook definitions of the word molecule can sometimes be a bit complicated, a molecule can be loosely thought of as a group of atoms stuck together, usually through chemical bonds. Here we see a single hydrogen atom traveling through the cosmos. It's made of one positively charged proton in its nucleus and one negatively charged electron. If our lone hydrogen atom happens to pass close enough to another lone hydrogen atom, their electrons, which are attracted like magnets to protons, can pull the atoms toward each other until they collide and stick together. The two atoms now share each other's electrons in what is called a covalent chemical bond. What were once 2 individual hydrogen atoms have now formed a single hydrogen molecule. This bond is not permanent. With enough heat or due to interactions with other molecules, the hydrogen atoms will readily separate once more. Different types of atoms can form different numbers of chemical bonds. A hydrogen atom can only form one covalent bond at a time. If a third hydrogen atom were to collide with a hydrogen molecule, it would simply bounce off, or if it hits hard enough or in just the right place, it can trade spots with one of the existing atoms. An oxygen atom can typically form 2 bonds. A carbon atom can make 4. An argon atom won't usually bond with anything. Even though possible bond numbers per atom are pretty small, huge molecules can form if bonds happen to be properly arranged. For example, even though hydrogen can only form 1 bond, a standard water molecule is always made of 3 atoms. This is possible because oxygen, which can form 2 bonds, forms just 1 bond with each hydrogen atom. A single molecule of the sugar known as glucose is made of 24 atoms, a special arrangement of carbons, hydrogens, and oxygens. A typical fatty acid in the human body may vary in length. This one here is made of 38 atoms. And finally, a single protein, depending on the type, can contain over 500,000 atoms all covalently bound together. The molecular models that I've been showing you here so far are what we call space-filling models. They show us roughly what the outside of each atom's electron cloud looks like, and different types of atoms have been assigned different colors. When we look at real molecules with a scanning tunneling microscope, they look pretty similar to these space-filling models, but the atoms are not color-coded and their edges are fuzzy. That blur is partly due to the microscope's limitations, and partly because atoms actually do have soft boundaries. When looking at complex molecules, space-filling models, and especially actual images of real molecules, can be a bit confusing to look at. Which atoms are bound together, which atoms are just close to one another. For this reason, chemists sometimes use what are called ball and stick models. These highlight the bonds between atoms, the skeleton of a molecule, instead of showing each atom's outside surface. In 2009, Dr. Leo Gross and his team at IBM discovered a way to take actual skeletal pictures of molecules. This is not a drawing, this is not a computer-generated model, this is an actual scan of a real molecule. Amazingly, atomic theory was allowing scientists to draw molecules with surprising accuracy over 100 years before this image was finally taken. That's quite a testament to what good scientific theory can do. When atoms come together to form a molecule, the molecule vibrates between its bonds in a regular pattern. You can think of the bond as a bouncing spring. This is because the protons in the nucleus of each atom repel one another, while the shared electrons in each bond pull the atoms back together. The vibrations we find in molecules are the result of a perpetual tug-of-war between these two forces. If you add more energy to a molecule with heat or light, the amplitude, the length of each vibration will increase without changing how frequently each vibration completes its cycle. This means the bouncing spring stretches further and the atoms move faster. If you add enough energy, the bond will eventually break. Scientists are fascinated by molecular movements and want to understand them better. These vibrations have a huge number of potential applications in chemistry, medicine, electronics, and computer engineering. Watchmakers, for example, use the unchanging speed of molecular vibrations to build watches that keep nearly perfect time. In a quartz crystal, bond vibrations between its atoms resonate, causing the entire crystal, when cut to the right size and shape, to oscillate microscopically at 32,768 times per second. Inside each quartz watch is a tiny crystal along with electronics that can count the crystal's vibrations. This then tells the second hand precisely when to move. In April 2019, in the journal Nature, Junhee Lee and his colleagues from the Center for Chemistry at the Space-Time Limit have published the first images ever taken of molecular vibrations at the atomic scale. Though these images may seem a bit strange to you and I, they show researchers exactly how this molecule bends and pulses between its bonds. Scientists can use images like this to build accurate models predicting exactly how different molecules will behave under various conditions. With this new precision knowledge, engineers are working on solar panels that generate far more energy, computer chips that do not overheat, and researchers are planning to use this imaging technology to better understand our own DNA. Even in a field as thoroughly studied as chemistry, the old saying is still true. Somewhere, something incredible is waiting to be known. So in summary, what is a molecule? A molecule can be described as a group of atoms stuck together through chemical bonds. Different types of group. In summary, what is a edible is waiting to be known. So in summary, what is a molecule? A molecule can be described as a group of atoms stuck together through chemical bonds. Different types of atoms can form different numbers of bonds. Molecules can be as small as 2 atoms stuck together, or, as is the case for some proteins, they may contain over 500,000 atoms all covalently bound together. Recent advances in molecular imaging are now letting us take snapshots of molecular vibrations at the atomic scale. I'm John Perry, and that is a molecule. stated clearly. Hello, you are watching Quick Definitions, stated clearly. What is an allele in genetics? As we've learned in earlier videos, a gene is a stretch of DNA, usually a long stretch of DNA, that codes for something. What exactly do genes code for? Technically, they either code for specific proteins or they act as templates for functional chains of RNA, but because proteins and chains of RNA go on to produce traits, things like eye color and bone length, we can say that an organism's genes, in a roundabout way, code for an organism's traits. An allele is an alternative version of a specific gene. If that sounds confusing, that's okay. It should become clear once we see a simplified example. Let's say there is a gene in a species of frog that codes for the frog's eye color. We will call it the eye color gene. No need to get too creative here. This frog has a version of the eye color gene, an allele of the eye color gene, that codes for yellow eyes. He has the yellow allele of the eye color gene. His buddy here has a different allele, a different version of the eye color gene. He has the red allele of the eye color gene. Now, this hypothetical example is overly simplistic. In real life, there are multiple different genes and sometimes environmental factors that all play together to determine an animal's eye color. Also, most animals have two copies of their own DNA, meaning that a single animal can actually have two different alleles or two different versions of any given gene in its own genome. Furthermore, most alleles don't have any actual effect at all on a creature's observable traits, but don't worry about any of these technicalities for now. The important thing to understand is this: an allele is an alternative version of a specific gene. That's it. New alleles, new versions of old genes, come into existence via mutations. Once a new allele exists, it is forced to compete with other alleles in the population. For example, when the yellow eye allele happened to emerge within our hypothetical frog species, it might have given its host a survival advantage because its host could better blend into its environment and hide from predators. Because of this, over many, many generations, the yellow allele could dominate the population, completely outcompeting the red allele, causing the red allele's extinction. When an allele dominates an entire population, we call this fixation. So there you have it. An allele is an alternative version of a specific gene. I'm John Perry, and that was a quick definition of an allele stated clearly. Hello, you are watching Quick Definitions. Stated clearly. What exactly is a fossil? A fossil is any preserved body part, excrement, or impression of an organism that lived in the distant past. This includes anything from a preserved footprint to a preserved foot bone to a preserved dino dropping. People sometimes argue over what distant means in this definition, but typically, if you find a bone that has been dated at over 10,000 years old, most people will be okay with you calling it a fossil. Fossils can be preserved in ice, river sediment, volcanic tar, desert sandstone, globs of hardened tree sap, you name it. If conditions are right, hard structures like bones, exoskeletons, or wood can sometimes go through a process called permineralization. They become permanently infused with hard minerals. This here is a Brazilian agate geode that I once paid far too much for at a gift shop. Agates are not fossils because they are not the preserved body parts, excrement, or impressions of an organism that lived in the distant past, but understanding how agates form helps us understand how permineralization works. In the distant past, this agate was a cavity, a simple hole in a rock, a bubble that formed in lava as it cooled. Rainwater slowly seeped through the lava rock and filled the hole, bringing microscopic minerals with it that were trapped as the water continued downward. When the mineral concentration was too high for the water to handle, the minerals crystallized, slowly forming solid rings along the inside surface of the cavity. As you may have noticed, bones and shells also have cavities, large cavities and microscopic cavities, that can fill with mineral-rich water. In this ammonite fossil, you can see that some of the large cavities are still partly empty. This was also the case with the agate, but other chambers are completely full. They are completely permineralized. This petrified wood became petrified when each of its microscopic cells were permineralized, just like the Brazilian agate. The same thing happened to the bones of this dinosaur. Not all fossils become permineralized, but those that do can then easily last for hundreds of millions of years. Fossil. Any preserved body part, excrement, or impression of an organism that lived in the distant past. I am John Perry, and that was a quick definition of a fossil, stated clearly. Thanks for watching. If you liked it, make sure to give a thumbs up and subscribe, because right now, I am publishing new quick definitions every other Monday. This video series is funded by good people like you who support me by contributing monthly to my efforts on patreon.com/statedclearly. If you'd like to help out, I'd appreciate it. So long for now. Stay curious. Stated Clearly presents... What is symbiosis? Normally when people talk about symbiosis, they're talking about two different types of organisms cooperating to help each other survive. For example, clownfish hide from predators among the tentacles of sea anemones. In return, they feed the anemone with their own droppings. Yum yum. The anemone and the clownfish enjoy a symbiotic relationship. In biology, however, symbiosis has a broader definition than simple cooperation. It's classically defined as any long-term living together of unlike organisms. Let me say that again. Symbiosis, the long-term living together of unlike organisms. Mutualistic symbiosis, or mutualism, is when both partners benefit from the relationship, like we saw in the clownfish and the anemone. When I say that both partners benefit from the relationship, what I mean is that both organisms experience a significant increase in evolutionary fitness. They both end up being better at surviving and reproducing. Parasitic symbiosis, or parasitism, is when one benefits while the other is harmed. Ticks are a good example of a parasite. They drink your blood and then sometimes repay you with Lyme disease. total jerks. Commensalistic symbiosis, or commensalism, is when one organism benefits while the other is not dramatically helped or harmed. Squirrels live in oak trees. They sometimes eat bark, leaf buds, and of course, they love to eat acorns. They consume the flesh of the oak tree's unborn children. This is great for the squirrel, of course, but surely this must be bad for the tree's evolutionary fitness, right? Well, multiple studies have shown that the relationship between oak trees and squirrels is both extremely complex and extremely ancient, apparently stretching back millions of years. Both organisms are trapped in an evolutionary arms race against each other. Through the ongoing process of descent with modification, acted upon by selection, oak trees have evolved many tricks to control the behavior and population size of their ancient, furry rivals. Among other things, the tree has evolved to produce toxins inside of its seeds. Squirrels, in return, have evolved a digestive system that can handle the toxins fairly well, but more importantly, squirrels have changed their behavior. When they find fresh acorns, instead of eating them, they stash them in shallow hiding places to let rainwater detoxify them over several weeks to several months. A single squirrel can make hundreds of stashes all over its territory every single year. If the squirrel dies before eating the acorns or simply forgets where some of them were hidden, the squirrel has, in effect, planted brand new trees, often in places far enough from the parent tree that there will be no parent-offspring competition for sunlight when the saplings begin to grow. This is called seed dispersal, and it's actually good for a tree's evolutionary fitness. It helps them produce more successful offspring. While it's difficult to perfectly calculate evolutionary fitness, there are so many unknown variables involved, it appears that right now, in the middle of this crazy evolutionary arms race, many trees either break even or sometimes experience an overall fitness gain when those pesky squirrels move into their branches. Here we see that there exists a symbiotic continuum from parasite to mutualist. Symbiotic relationships can and do change dramatically over time. Even ticks, which almost all of us consider to be horrible parasites, when they're not carrying diseases, sometimes act more like commensalists than parasites. Due to their small size, they take very little blood from their donors. This means that a single tick won't usually cause a noteworthy fitness decline in its host. Results from a recent study show that possums may actually benefit from tick infestations. This is because they snack on ticks, and a single possum may eat over 5,000 ticks per week during tick season. Now, ticks are really small, but 5,000 per week, that is a noteworthy supplement to the possum's regular diet. Ticks are sort of like little sack lunches that come directly to you, free delivery. It might seem silly that biologists invented a word, symbiosis, to encompass everything from parasites to cooperators, but the reason for this is that parasites can evolve to become cooperators and vice versa. Understanding these evolutionary transitions is fascinating, but more importantly, this knowledge is now helping us control diseases. For example, many of the bacteria living in your intestines actually help you digest your food. They eat the parts of it that you can't absorb, and then excrete the waste products that you can absorb. Yum yum. Most of the microbes living inside us today either have a mutualistic or a commensalistic relationship with us, but some of them started out as parasites. In 1991, a bacterial intestinal disease called cholera broke out in South America. As you may know, cholera causes extreme diarrhea. That's why it's so dangerous. It makes its host desperate to use the toilet and then spreads to new hosts either through dirty drinking water or through person-to-person contact. Biologist Paul Ewald studied its spread and the evolution of the cholera bacteria in real time. In nations with bad water filtration, the bacteria remain deadly year after year. This is because natural selection favored strains of the bacteria that would make people use the toilet more frequently, even if it eventually killed them due to dehydration, because the bacteria would contaminate more water this way and spread faster to new hosts. In countries with good water filtration, strains of the bacteria evolved toward commensalism. In these environments, Natural selection favored microbes that were, quote, kinder to people because people were then healthy enough to go to school, to work, and mingle with friends and family. This allowed the bacteria to spread slowly and non-violently through human-to-human contact. The take-home message here is this. When there is an outbreak of cholera, not only should we immediately treat the sick, we should also distribute clean drinking water. Doing so will guide the bacteria's evolution in a direction that's good for the future of the people in the area. These fascinating interactions and evolutionary transitions from enemy to friend and sometimes from friend to enemy are all possible because of symbiosis, the long-term living together of unlike organisms. While most people have no trouble understanding how evolution causes animals to adapt to their environment, a bear to the cold, for example, we often forget that a creature's environment also includes the other organisms that share that environment. If two species live together and interact long enough, the slow process of evolution, descent with modification, acted upon by selection, can cause living things to evolve and adapt to each other. I am John Perry, and that is symbiosis, the long-term living together of unlike organisms, stated clearly. For those of you who speak Spanish, make sure to stay tuned at the end of this episode. We now have a brand new YouTube channel for Spanish videos only. You are watching Quick Definitions, stated clearly. What is horizontal gene transfer? Most of us are used to the idea of vertical gene transfer, that is the passing down of genes vertically from parent to child. Hopefully that's all pretty straightforward. In contrast, horizontal gene transfer, sometimes called lateral gene transfer or sideways gene transfer, is exactly what it sounds like. It is the passing of one or more genes through routes other than parent to offspring. Horizontal gene transfer is fairly common in bacteria. Some types of bacteria do this by actively attaching to and then sharing genes with other bacteria around them, even completely different species. Some bacteria can collect genes that have leaked out from other cells, use them as their own, and if all goes well, pass the foreign genes on to the next generation when they reproduce. Because of this, once a gene for antibiotic resistance evolves in one species of bacteria, it can quickly spread to others, which causes huge problems for us when trying to control diseases. Horizontal gene transfer is common in bacteria, but for most plants and animals, complete horizontal gene transfer appears to be very rare. With a few exceptions, every cell in your body contains its own full copy of your genes, your entire genome. The same is true for other multicelled animals and plants. Because of this, everyone is constantly spilling genes when cells die or are damaged. As you bump around through life along with other organisms, your pets, random bugs, bacteria, plants, and so on, it's fairly likely that at some point, genes spilt from someone else's cells will wind up getting inside one or more of your cells. In most cases, this is not a big deal. You have special enzymes that usually destroy foreign genes on entry, but recent studies suggest that in rare cases, foreign genes can physically fuse with your cell's DNA. At this point, your cell behaves as though the foreign genes are its own genes. It can start reading them and using them to make proteins. Certain types of viruses reproduce by forcing this to happen. They actively insert their genes into the genomes of their victims' cells. Scientists now know that interspecies gene swapping happens all the time, but from an evolutionary perspective, it really doesn't matter if one skin cell or one eyeball cell happens to take up a foreign gene. It only counts as complete horizontal gene transfer. It only affects evolution if a foreign gene ends up making it into a reproductive cell. That would be sperm or egg in animals. That would be a gamete inside a pollen grain or ovule in plants. Then, one of those reproductive cells has to actually go on to make a child. That child would then contain the foreign gene in every cell of its body, and it would pass it on to future generations if it one day succeeds in having offspring. As you might imagine, complete horizontal gene transfers in plants and animals appear to be very rare, but when they do happen, they allow genes to hop from one species to another, from one closed gene pool to another. This, along with normal mutations, gives natural selection brand new toys to play with. It's currently unclear how important horizontal gene transfer has been in the evolution of humans. Here are 2 papers on the topic that completely contradict each other. But we do know that horizontal gene transfers happen naturally, even in our own species. I'm John Perry, and that is horizontal gene transfer, the passing of one or more genes through routes other than parent to offspring, stated clearly. Alright, here in a moment I will introduce you to our new Spanish channel, but first, a quick shout out to viewers like you who are financially supporting our animations on patreon.com/stated clearly. Thank you, I could not do this without you. Stated Clearly is It's funded by our viewers on patreon.com/Stated Clearly. Stated Clearly presents Where Do New Viruses Come From? If you've been watching the news, you've probably heard of the novel or new coronavirus, which, starting in late 2019, began making people ill in China. International air travel has since allowed it to spread person to person to new countries, as governments began to issue travel restrictions and even quarantines. Speculations about the origin of the virus began to spread online. Some claim that the virus might be a genetically modified weapon, but extraordinary claims require extraordinary evidence. This claim currently seems highly unlikely. Others suggest that the virus may be an escaped lab specimen. Now, this actually is possible. Viruses have escaped from research labs in the past, but as of the time that I'm recording this voiceover, investigations into this idea have not yet reached any solid conclusions. Could there be another, more natural explanation for the origin of this virus? The answer is yes. COVID-19, the new human-infecting coronavirus, may have simply evolved from an older animal-infecting coronavirus. To understand how this may have happened, let's first take a look at viruses in general. What are viruses? Of the many things that can make you sick by infecting and reproducing inside you, viruses are among the smallest. If we resize this drawing to a more realistic scale, you see that hundreds of viruses can fit inside a single bacterial cell. That's how tiny they are. Thousands of different viral species have been studied and described by scientists so far. Millions more likely exist. They come in many forms, but all species consist of a small collection of genes, stretches of either DNA or RNA that carry information for making more copies of the virus, and those genes are enclosed in a protective coating of protein and sometimes a lipid membrane. All known viruses are parasitic, but most are not parasitic to humans. Instead, some only target plant cells, others only infect bacteria, and so on. A virus reproduces by getting its genes into a living cell. Different viruses do this in different ways, but once inside, the cell acts as if the viral genes are its own genes. It begins reading them and building copies of the virus instead of performing its normal tasks. Coronaviruses are a huge family of virus species that infect animal cells. Some infect chickens, others infect pigs, some infect humans, but most of them are extremely mild. They simply give you the common cold. Corona means crown and refers to the unusually large crown-like spikes sticking out of their membranes. These protein spikes are selectively sticky, sort of like Velcro. They don't attach to most objects, but are extremely sticky when they bump into specific molecules found on the outsides of animal cells. Once held firmly in place, the coronavirus waits until swallowed by the cell. It then begins to reproduce at the cell's expense. Different animal species have different types of molecules on the outsides of their cells. Because of this, bird-infecting coronaviruses usually can't infect humans. Their Velcro doesn't hold strong enough to our cells. Unfortunately, the natural process of evolution can sometimes help a virus overcome this problem. When virus genes are being copied during reproduction, mutations can occur. These are either due to simple copying errors or processes called reassortment and recombination. These happen when two or more viruses infect a single cell. In most cases, mutations that change the shape of viral spikes render the virus useless. Their Velcro no longer sticks to any host cells. On rare occasions, however, a chance mutation will just happen to allow a virus to attach to a new host species. If the modified virus is then lucky enough to encounter that new host species, infection can occur. We call this a spillover infection. The virus has spilled over into a new type of host. Early on, during a spillover event, the virus usually isn't very good at infecting its new host. Its Velcro is not a perfect match, and many other challenges might slow the virus down. Oftentimes, the mutations that let it infect the new host also make it worse at infecting its original host. Because of this, many spillover viruses go extinct after infecting just 1 or 2 people. They're usually dead ends. That said, if the virus can survive and reproduce just long enough, natural selection will promote any new mutations that help it better spread and reproduce in the new host population. Positive mutations accumulate over multiple generations, negative mutations are discarded until, bam, a new epidemic is being screamed about on the news. Though it may seem to us that these new viruses just sort of pop into existence overnight, scientists now know there is a long, slow burn before each explosion. Genetic evidence tells us that slowly evolving spillovers have been the cause of almost every major outbreak known in history. In the early 2000s, a coronavirus that used to only infect bats appears to have spilled over into civets. There, it mutated even further and spilled over into humans. We called it the SARS virus because it causes severe acute respiratory syndrome. It spread internationally from person to person, and several scientists were infected in the lab. By the time the virus was contained, over 8,000 people had been infected, over 700 died. A coronavirus from camels also recently spilled over to humans, causing even more deaths. Coronaviruses are not the only types of animal viruses that can adapt to new hosts. HIV spilled over from chimps, most likely when someone cut themselves while preparing chimp meat for dinner. The swine flu came partly from pigs, but we think it actually evolved through a recombination with a pig virus and a bird virus. The 1918 Spanish flu, the big one that devastated populations all around the world, may have spilled over from chickens. While the evidence is not yet conclusive, the new coronavirus might just be one more example of normal evolution. A very similar virus has been found in bats, and another was recently discovered in pangolins. These animals are endangered, they're protected, but they're often used illegally for food, rituals, and alternative medicine in the region where COVID-19 first broke out. Now, there are serious people checking to make sure that the virus did not come from a lab, either by accident or on purpose. After all, the technology to genetically modify viruses really does exist, but it's important to understand that the normal process of descent with modification, acted upon by natural selection, really does produce new viruses. It happens naturally. The chance of a virus evolving to successfully infect a new species is extremely low, but there are over 7.5 billion people on this planet. Most of us interact with animals on a daily basis. We keep them as pets, we eat them as food. This means that as unlikely as spillover infections might be, there are billions of opportunities for one to take hold every single day. Add this to the fact that the entire world is now connected through international flights, and you realize that what happens in Vegas doesn't actually stay in Vegas, at least not the way that it used to. Luckily, we have international groups like the World Health Organization and various centers for disease control to help contain outbreaks when they happen. With international cooperation, we have prevented many catastrophes in the past, and we will prevent many more in the future, so long as our species continues to work together. So, in summary, where do new viruses come from? In most cases, new viruses evolve from old viruses. Stopping the spread of new viruses requires international cooperation. For up-to-date, accurate information on the risks, visit the World Health Organization website at who.int. I am John Perry, and that is the novel coronavirus, stated clearly. This episode of Stated Clearly was funded by our viewers on patreon.com/Stated Clearly. If you found this video helpful, please do consider contributing there as well. Aside from helping me out, you will also get secret access to a Stated Clearly animation that is no longer public. It's actually the first one that I ever made, and, well, you'll see. To learn more about evolution and to find free tools for use in the classroom, if you happen to be a teacher, high school, middle school, college, visit our website at statedclearly.com. So long for now, stay curious. Hello, good people of the internet. John Perry here. I am the creator of the Stated Clearly YouTube channel, and today is Darwin's birthday, and so I'm doing another Darwin Day special. Now, normally I try to get out and do a talk somewhere and record that for you, but it's COVID, so I'm going to be doing this from my own office, from my house today. Hope you don't mind. Behind me, I've got a drawing of Chuck himself, which I made. I drew that back in 2010 when I first decided that I wanted to teach evolution. I drew that while thinking about how I'd do it. I wanted to, make a career shift. And Stated Clearly was the idea that I came up with while I was drawing that picture. And just to kind of celebrate this, it's Darwin Day, and it's been many years since I started this channel. I just put a version of that, a poster version of that drawing in the store on YouTube's little store there. So if you want, you can support the channel and get a cool Darwin poster. This talk is actually pre-recorded. I did that just, I like to pre-record things before I put them on the Stated Clearly channel. But I do have a live question and answer session, which will start after this video is over. And there's a link to that in the video description. That's on my second YouTube channel, the Stated Casually YouTube channel. A lot of people, I noticed, don't know that I have a second channel. So yeah, go over there and subscribe to Stated Casually if you have not already. And I made that channel because doing animations takes forever, and I wanted to have a place where I could upload more frequently. I'm currently doing at least once a week over there. Actually, I've been doing twice a week over there. So if you want more biology stuff, subscribe to the Stated Casually YouTube channel. And that is where we will have the live question and answer session after this broadcast. So, today's talk, lecture, whatever you want to call it, is: can we test the theory of evolution? I've noticed since I started teaching evolution on the internet that there are a lot of people that are very skeptical of the theory of evolution. They don't want to just trust scientists who tell them that evolution is legitimate. And, say what you want about the doubters, people who doubt experts, but that really is, doubt, suspicion. This is actually an important part of science. The Royal Society, their logo is, or their slogan is, nullius in verba, which means take no one's word for it. People who are skeptical of evolution are following that advice. They want to take no one's word for it. And so the question that I want to address today is, can we actually test evolution on our own? Like, even at home during COVID-19 lockdown, can we test evolution ourselves and actually see whether or not it's a good theory? This theory that Darwin produced so many years ago now. And the answer is yes. But how? How is it that we go about doing that? This here is Imre Lakatos. I like saying his name. He's Hungarian. He's a philosopher of science. He came after like Popper and those guys. He talks a lot about how to best test a theory, and he really focuses in on research programs. If you want to test a theory, what you need to do is build a research program. You use the theory to make testable hypotheses, and then you go out and you try to test those hypotheses. You go out into the world and you test those. And if the theory that you're testing, you're studying, is a good theory, many or even all of those hypotheses should end up leading you to new information. Those hypotheses should be proven to be correct. And the reason that you can't usually just test a theory directly is, a theory like evolution is an extremely broad, overarching theory. And it's actually hard to directly test the theory itself just because it's so big. People have talked about ways to falsify evolution. It's certainly possible to think of things that would falsify the theory of evolution if those things happen to be true. But it is pretty difficult to really directly test a theory as broad as evolution. So he says, use the theory to design a research program, make testable hypotheses, go out into the world and test those hypotheses. And that might seem a little bit abstract. Don't worry, I'm going to give you some concrete examples. I actually did this when I first started learning about evolution. I actually tested my own hypotheses for the same reason that a lot of people want to test the theory of evolution themselves. A lot of people who are writing me. I was told when I was very young that the theory of evolution was wrong not only was it wrong, but I was told that scientists were going to try to trick me into thinking that it was correct. I learned this at Sunday school. And when I first learned about the theory of evolution, I was very curious. I wanted to understand it. Before you can test a theory, you have to really understand it. So that's the first step. Actually know what it is that you're testing. A lot of people who, you'll see, anti-evolution blogs where people are talking about, evolution has to be false because of this and this and this. More often than not, they don't understand the theory of evolution. They're seeing things in nature that don't mix with their fake version of the theory of evolution that they have in their head, and they think that they've somehow debunked the theory of evolution. In order to really test the theory, you have to understand it first. And I was aware of this. I was 12 years old. When I first learned about evolution, it was from a documentary by David Attenborough. So, I had learned about it at church, but the first science educator that taught me about evolution was David Attenborough. And the things that he was saying, they made sense, but I was very skeptical. I thought he was one of these bad guys that's going to try and teach me bad things and get me to believe a bad theory. So I wanted to find a way to kind of test this on my own. And the first test that I came up with was based on something that I had noticed years earlier. We got a dog when I was probably 5 years old. His name's Chester, little fur ball, and he was like my best buddy. I loved this guy. I spent a lot of time with him. Before Chester, we didn't have pets. I would play with bugs and stuff in the backyard. So I noticed a lot of things about bug anatomy playing with them. And then I started paying pretty close attention to my dog's anatomy. And one of the really cool things that I noticed is that his skeleton is almost exactly like mine. And there were a bunch of really cool things about this. That I noticed that he has this backwards looking knee sort of thing. It wasn't actually a knee, that was his heel bone. That dogs walk on their tiptoes. And I noticed that his back legs are attached to hip bones, just like mine are. And his front legs, surprisingly, were attached to shoulder blades, just like my arms are. And so I realized that my dog's front legs are the same as my arms. That was really weird. And so when I learned about evolution from David Attenborough, watching this nature show, that was the first thing that I thought about. And I thought, okay, if I want to test this theory, I don't want to just trust what David Attenborough is telling me. I don't really trust this supposed expert. What I could do is I could make a prediction. So I know that I have hips and shoulder blades. My dog has hips and shoulder blades. If evolution is true, maybe the reason that I and my dog both have shoulder blades and hips is because the common ancestor of all mammals had hips and had shoulder blades, and we just inherited that through, a historical accident, if you will. And so what I did is I opened up the encyclopedia and I looked around for, I looked at skeletons of different animals in the encyclopedia. And what I found was that, in fact, all mammals, they have shoulder blades in the front and they have hips in the back. So this is actually a picture I took at the Natural History Museum in Oxford. You've got, we've got I think that's a lion in the front there on the left. You got some sort of a pig there. Tapir with a crazy looking nose. And you've got a giraffe in the back. All of them have the same basic body plan and the shoulder blades in front and the hips in back. And I noticed this, when I was younger. I didn't have internet back then. I noticed this in the encyclopedia. And that, of course, wasn't a total confirmation of the theory of evolution, right? That was just one thing, one testable hypothesis, and one confirmation of the testable hypothesis. But it gave me confidence in the theory of evolution, a little bit of confidence in the theory of evolution. But it was, of course, possible that maybe there's a reason aside. Aside from common ancestry, that animals have these shoulder blades in front and hips in the back. And so, as the years went on, I continued thinking about evolution. I continued trying to make little hypotheses and, testing those hypotheses. And the next big one, if you really have been following my work lately on both of my channels, you've probably heard me talk about this before. The next big prediction that I made had to do with stingers in bees. I had captured a bug in the backyard, a katydid, and on the back of that katydid there was a long stinger-like structure. And I freaked out and I dropped the thing on the ground because I didn't want to get stung. I had been stung by bees before, right? I was in high school at the time. I went to my biology teacher. I asked my biology teacher, do katydids have stingers? And he said, no, but they do have ovipositors. Females have ovipositors. And what they do is they stab into the ground and they lay their eggs with these ovipositors. So ovo is egg and depositor, egg depositor. These are egg depositors. So here's a photograph of a katydid stabbing the ground and, laying eggs in the ground. I thought, oh, that's interesting. I wonder if a bee's stinger is a modified ovipositor, because the ovipositor looks a lot like a stinger, right? It excretes eggs, and I also read about it in a bit, and they also excrete little fluids that help protect the eggs. And I thought, well, maybe since, bees don't, most worker bees don't lay eggs anymore, maybe there's the fluid that would come out of the ovipositor, maybe that had transformed over evolutionary time, it evolved to become a venom-like fluid. And so you turned a reproductive organ into a weapon. And to test that hypothesis, I asked, do male bees have stingers? And I was able to look that up in the encyclopedia. Now, again, these are not new discoveries to science, but they were new discoveries to me. I didn't know these things. I predicted them based on the theory of evolution. I looked them up, and sure enough, they were true. Male bees do not have stingers. I looked even further. Internet was around at this time, and I learned that actually scientists classify the bee stinger as a modified ovipositor. And if you look at the history of its evolution, it actually, here's a close-up of a stinger, of a queen bee actually laying an egg, and she's using the stinger. It's kind of hard to see. She's actually using her stinger kind of as a finger to move it around inside of the egg chamber. So the egg doesn't come out of the stinger in bees, but they do use the stinger to help deposit eggs. Even still, the queen bee does. She can actually sting with it too. Her sting is not quite as bad as the worker bee's sting. I've highlighted the stinger in yellow here so you can see it. It's kind of hard to tell in this picture. The male bees do not have stingers, and it turns out that the venom in a stinger appears to have evolved in the earlier ancestors of bees, which were doing what wasps still do today. They would lay eggs inside of living animals. And so the venom evolved to help with this, to subdue their victims. This is a caterpillar that's being stung by a wasp, who is then going to lay her eggs in that wasp. And here is a clip of eggs hatching out of a caterpillar. So that is horrible. We now have two hypotheses that I was able to make based on the theory of evolution. I was able to go out into nature, read about nature, and learn that, in fact,
Oh fuck, I forgot my desktop audio on. That is bad. There should have been a bunch of audio of my videos. Anyway, there is no soul capture on this thing, apparent. So if I use it now, I'll get shitty mixed by the poison. So you know it. Fuck, I forgot to look at that chow. So, there is no eggs for sale here, and I have to drop it on this damn thing. Furthermore, there is the problem that I have not seen capture on this game. Can I capture this soul? Can I return to this boss easily? It's like a lot of problems here. I'll probably not drop it. I've never dropped one of these shits. And that will be it. Not coming back. At least for now. Know the buff. It's not the also from the pores. If I try to walk and get locked, I'm fucked. If I just ignore this, it will fuck me into the cost of the farm. Ouch. That not doesn't hurt so much. Can go back then. They are harmless to me, basically. Now I have to do this stupid challenge. We go on very badly together. At least try to drop. The drop chance on this squad is hated at 0.4%. That it's the double, the original drop chance, I think. And what the fuck just happened? I did nothing and I died. Full game. Oh, this thing took action points away from me. What the fuck? I never realized it. That was possible. That was an actual strategy. Cool. Just a moment to learn. Now let's kill shoot. Have to kill it. Peg. Kill this one, but no range, no way to get that. My stupid crowd does not work properly. And the fucking boss can get me. Think to throw me at this wall. Throw me down. Really choice. Now I cannot attack. Oh shit. Danger, piglet. I'm going for it. Oh, I should have shoved it. Over. Now, it's cooperating with me. Oh, I can kill it, but I can do nothing else. Because the thing does not max. That does not seem right. I fear it is not a wise choice. And who I have to kill now? I have to kill the other one now. Now it tells me that one. The fucking pig is coming at me up. It keeps taking my movement points every time, and is right? The cooldown broken too. Okay, I have to attack that fucking pig. But if I do that, it dies. Oh shit. Oh shit. Did not die. So sad. Sad Yosa Moda's noises. It tells me to attack the pig. Even if I could walk, I would not use my stuff. The shoving mechanics is broken, it's hitting too little. Tsururu, if I put poison, we would fail the challenge. Oh my god. I have to extract the Osa from over there. I can walk. Go for the Osa. I have gone for this one, perhaps? Well, it clearly did not. Is that shot, right? Yeah. That's it. Just wait now. Gustavo Lopes. Tá usando a conta do teu irmão, caralho? Oh, I have to kill the pig now. What a pleasant surprise. Oh, what's the other? Fuck me dead. I am afraid if I shove it, I might kill it. Sad pig noises. I cannot fucking move. I should say cool. Another pig. I was about to kill it, but that's the challenge. Keep me doing that. How have I not failed this shit yet? Good. Now it's gonna be the pig now. Bacon. Here comes the egg. did not die. So many achievements. No egg. Well, this pays for the key, so it's basically free to run it. Just takes time. Oh.